All right, so we're 10 minutes past, and I'm really hoping not to go over 1 hour in these, so I'll begin. Um, and I'll begin by introducing myself I mean, I don't need to introduce myself to Louisa and Varjan, but most of the rest of you I don't know. So my name is Babar Ali, and I am one of the staff scientists at IPAC. And last year I had my one and so far only NITARP team. And before then I sat with Louisa's team on Seaways, and got the hang of what it's like to run people from high school and colleges to go through a full NITARP science program. And one of the things I realized is that we emphasize a lot of science. We teach you a lot of science, but one important component of science is programming, and that's really sort of something we don't do, or we didn't do it for many reasons. So one is simply the crunch that we have, putting everything, the whole project from the start to the end in 1 year. And secondly, there is a little bit of startup time and a little bit of learning time for programming. When I went through graduate school, I learned Fortran. And Fortran, as you will learn later on today, is the type of language that's the lower level than Python. Much more difficult to learn, initially at least. You have to get used to a lot of nuances of Fortran. And then you have to learn how to compile it optimally and do all sorts of things like that just to get going before you can do anything cool with the program. So that was sort of my experience and what was in my head until things like Python started coming around. And now there's a real chance that you can actually teach Python or use Python to get people into programming. So last year, I actually I learned a lot by teaching, and I think that this time around it will go a bit more efficiently. But everyone liked it. Not everyone was able to use it, but I think I know why. So we'll try and rectify that this time around. But it was clear that this is something that was very popular and something that was welcomed. And one of the students, in fact, told me that she hates computers, she hates programming, but this is the part that really she enjoyed the best about the NITARP, and now she's programming in Python. So who knows? Anyway, that's sort of my long drawn introduction to this course, to me, to the motivation behind it. Hello? Okay.
You can mute, please, if you're not actually speaking. It will help cut off down the background noise. And Babar, are you recording this?
This is being recorded, yes.
Excellent. Okay.
Thank you, Louisa. Yes, I should go over a couple of etiquette points. It's really helpful if you mute, and that is not to say you shouldn't unmute immediately when you have a question that that you wish to answer or ask. But do mute while I'm talking or somebody else is talking. That said, I should also mention that if even if you're not familiar with WebEx, or if you are familiar with WebEx and you know how to chat on WebEx, while I'm presenting, I can't actually see the WebEx console. So you would actually need to use the audio link to get my attention. And then I can go and see if there's anything that I need to see there. But please use the audio link to ask the questions. All right, let's jump right in. Programming with Python for non-programmers. So the greatest thing about Python is that it cuts down so much of the overhead in learning how to build the very basics of the program, like telling computer where to store a number and then manipulate that number. Python has made it really easy or relatively easy for everyone. And it's being used everywhere. I mean, those Lego robotics, there's now a Python module for that, and you'll learn what modules are later in the course. So you can program in Python and start controlling those Lego bots. So it's very far-reaching, and because it's easy to use, it's becoming more and more involved or expanded to other applications. All right, so okay, why am I not going? All right, so today I don't know if we're actually going to get to programming in Python. You'll get to hear about Python, but this really is a course for non-programmers, and so the first most of today we're going to talk about what programming is. And go through some very introductory concepts, and certainly I'll introduce the differences that Python has within these introductory concepts compared to other programming languages. And then at the very end, if we have time, we'll actually get to see Spider and Python, and we talk about Anaconda. I also want to take the time today to go over any questions you have about installing Python and Spider and Anaconda. Any issues with that? And if you're connected on the WebEx, which you should be, I can actually view your desktop and help you debug any of the issues with the installation. But apart from a couple of emails, most of you seem to have gotten that part right, or haven't had any issues with it. So I'll assume that most of you are actually set up with Python. Okay, so today, what is a program? Why program? When you should not program? And then you take apart a program, what do you find? What are the various components of it? Okay, programs. So this is, you can go to Merriam-Webster or you can go to Encyclopedia Britannica, but a program, and I'm not trying to insult your intelligence there, I'm just trying to be more tuned to to our concept of the program here. Here, what we mean really is controlling the computer, okay, getting it to do our bidding, and we do this with a sequence of coded instructions, and that's all a program really is. This slide didn't reproduce very well, and I apologize for that, but this is sort of a way of thinking about a program. And I think when I first started looking at programs, flowcharts really were the best way to think about how to set up your program. Now, in reality, or in practice, they've sort of gone out of vogue. No one uses flowcharts anymore to think out how they're going to program the computer. But this is sort of going back a few years, and what you would have learned if you have taken a very beginning programming course. Okay, the reason, and this is a very simple program, and all it does is checks to see whether or not your thermostat should be on or off during your house. And in fact, this is so simple that most modern thermostats don't even work this way. They actually look at the history of run and everything else. But this is a good illustration. And if you walk through it, all it is a series of if, then, and block executions that essentially build the logic of the program. So you start by reading a temperature setting. Can you see the mouse when I move the mouse?
Yes.
Okay, very good. So this block, this very badly formatted writing block, all it says is you start by reading the temperature, okay? And then you follow the arrow, which is the flow, the execution and of the code, and it says, now you also read the room temperature, okay? One of them you store in a variable called T, for example. The other one you store in a variable called R, okay? The next thing you do is you compare the two. Is T less than R or equal to R, okay? You always, when you want to do these branches, you always want to have a yes or no, and no ambiguity there. So is T less than or equal to R is absolutely not ambiguous, and you can only have a yes or a no answer. So depending on what your answer is, okay, you either turn the heater off or you turn the heater back on, and then you go back to where you read the room temperature, or even if you want to go back to thermostat temperature, but you go back and repeat the process and just again. Okay. Now, if you looked at the wiki, you'll find that I've left an exercise for you. And this is essentially what I'm looking for in that exercise. Can you write down a flow chart of how to sort numbers and get to the maximum, or just even how to get to a maximum without the need to sort or do anything like that? Okay. And I'll post the solution in the next couple of days, so you can compare and we can go over it. But this is what I'm looking for. And again, the whole point is that it logically organizes the program in your head, and it helps you think of the program or better understand what the function of the program is and what programming is all about. Okay. So this slide, I'm just repeating what I just said, which is you control the computer. The thermostat in the previous example was our computer, whether it should be on or off, and you control it with the programming. What you used in a thermostat is, or how you interface with the thermostat is pretty simple. You select the dial to the temperature you want, and that's your setting T. Okay? And then the programming is behind it, and we don't really deal with the programming. Somebody has written that program and put it inside a little microchip in your thermostat that is now constantly running as long as it has power. What people use for that is different. They don't necessarily use Python for that. In fact, they usually use some sort of a lower language. And that's where the first thing about programming comes in, is that we're using a language which is at a much higher level than what computer understands. Okay, the computers are essentially built at the very, very core CPU level on something called a machine language. Machine language is very complicated, but it's a series of yes/no instructions, and these instructions get, each one of these yes/no is an answer to some very basic question, like, is the letter A? Okay. And these instructions are very basic instructions. These are the ones that billions or millions of them are executed per second within the in the CPU itself. Okay, we don't necessarily want to deal with such a fundamental level. Okay? In fact, machine language becomes very specific and sort of connected to the actual hardware, how the chips were built. Okay. And so it would be very different if we were talking to an Intel chip or an x86 old IBM or a PowerPC chip. Okay. All of them are different system or different architectures for the CPU, and they all will understand slightly different set of questions. Okay. And it's so inefficient to use it that it was quickly apparent that you never really want to use machine language for everyday programming. And so there are these layers that built up on top of that have slowly been building up even more and more, and I suspect will continue. And that's where Python really comes in. So this little pyramid that I got, it's again an old copyright-free image, and in that image you see the various sort of layers of the computer languages. You start off with the hardware, machine language that controls the hardware. Assembly language is very similar to machine language. And then the next level, this is where it really starts to get interesting for us. At the higher level languages, you start getting into C, Fortran, Pascal. If you've never heard of this before, that's okay. They're basically some of the first computer languages that at that higher level, where you could write things that look more like English and math, or a combination of English and math, but it was intuitive and it was something that you could easily understand. These instructions are then basically parsed down into something very basic. The series of yes/no questions that a computer answers and then does whatever it's supposed to do by the program. Okay, and so essentially, we build translators. Okay, we wrote in something that we were comfortable in. The role of the translator was to then convert it into something that the computer could understand, and then both were happy. But just to give you an idea, this is the assembly language code, and all it does is it prints "Hello World." And this is again meant to be an illustration, so it has a bunch of comments. Again, a concept that I'll come to in a bit. And the only thing that you should really get out of this slide is a lot of non-intuitive calls. Okay, whoever wrote this code wrote these comments that explain what this call is doing, but none of this, if you looked at it, would be obvious to you what it's doing. Okay? And this is what you would have to do. And if you were to print "Hello World," which is what this does, you would set up everything prior to that, just so you can get to "Hello World." If you wanted to print something else, you would set up everything else again, and then have it print out whatever other sentence you wanted to print out. And things would change, okay? Like "Hello World" is certain characters long. If your sentence was different characters long, you would have to define things slightly different in the entire preamble leading up to "Hello World." Okay. So again, we invented the high-level programming languages because that's really much more intuitive. And I think I've spoken enough on it, so I'll just jump ahead and tell you one more, introduce the compiler. Okay. A compiler is that translator. Okay. If you hear me use the word compiler, that's what I mean. It's just nothing more than a translator. The source file is where you write something that, the logic of the program in a language that makes sense to you. Okay? The compiler will take that and then it'll turn it into something called an executable. And that executable is what you would run and the computer would understand. Okay? And so would the executables look different from architecture to architecture? The answer is yes. So if your source file may look exactly the same, okay, the translator knows what language it needs to translate to. So an executable that you use a compiler to build on a Microsoft system will not be understood by the Macintosh system because the underlying hardware and the architecture is slightly different between the two. Okay, so I've been talking for a while. Any questions? Okay. All right. Okay, so now let me show you what "Hello World" looks like in C. This is for this "Hello World" code. The assembly language is written for an x86. If there was a different architecture, all of the preamble would look very different. Okay. In C, this is what "Hello World" would look like, but it would be the same file on all different architectures. So you could write this "Hello World" on Microsoft. You could write this "Hello World" on Mac or Linux or any of your preferred devices, including, say, your iPad, if you wanted to. But in C, this is what it looks like. It's still not entirely intuitive, but it's a lot better than what you saw with the assembly language code. Okay, it has a few components that need declaration. Essentially tell the computer, okay, I'm starting a program. That's what the main statement does. Okay, and I'm going to need some additional functionality for this program, mainly input-output functionality. And then here's what I most like you to print out on the screen. Okay, it sort of makes, this is more closer to English language. So print is there. We know what print means. It's not exactly just print, it's print out, but here. Once you have written this series of instructions, you would then need to activate the compiler. And usually that means that you get onto the command line and you issue certain commands for the compiler. And this right here, gcc-o hello world.nc hello world.c. That's one way of compiling this code, okay, basically running through this yellow compiler and getting out an executable at the end, which would be the hello world executable. Then you simply run the hello world executable, and on your screen, hello world would appear. Okay. Now, there's yet another layer, and that's where scripting languages come in. So the compile languages, like the C example I gave in Fortran, which I learned in grad school, C++, which is a slightly different flavor of C, those are all languages that need that compiler. Okay. The advantage you get is that they're actually very fast. Okay. If you are going to, say, for example, compute 1,000 times, okay, the average of some number of values. Okay. If you used a compiled language like C or Fortran or C++, it would be much faster, okay, than something like the scripting language, which we will get to. But that's one of the main advantages of the compiled languages. Okay, the drawback of the compiled languages is that the syntax is harder, relatively speaking. And to optimize the compiling, you really it can get a bit cumbersome. There could be subtle differences in the computer architecture, whether, how they write a basic byte, whether they write the biggest number first or the littlest or the smallest number first is, could be difference between the two. And that kind of detail makes the compiling not work sometimes. Okay. So you want to use it for speed and a little bit more flexibility, but be prepared to pay for it in more tedious compiling work. Okay. The scripting language is yet another layer built on top of the compile language, and this is where Python and Perl come in. And basically, the compile is constantly running for those languages. And so all you have to do is issue the simplest instructions, and then they fall down to the next level, which is at the compile level. And from there, they fall down to the next level, which is at the assembly level. And then from there, you can control the hardware to do whatever you want. Okay. And so your interaction is at the highest layer in this space. Okay. And in fact, that is the biggest advantage of these scripting languages. They're extremely easy to use, okay, as we'll see. But the price you pay is that they will be much slower. Okay. And you can't do as much with them because when you turn the compiler on, you have to make a certain assumptions about how you're going to use the scripting languages. Okay. So obviously Python is an example of a scripting language. And now when you want to do the hello world, all you have to do is issue print hello world. Okay. So compare that with C. Okay, you have to write the code. So that's the code right here. And you have to compile it, and then you issue it, and you get that. Python, hello world, right away. Okay. So you should, at this point, have gotten sort of an idea of where Python sits in terms of computer languages. Any questions on this? All right. So I'll go concept. Again, I'm assuming you have, you don't, this is your first introduction to programming, so we'll really be talking about the fundamentals of programming before we even get to Python. So they're written essentially as text files. Okay, print hello world, for example, just nothing more than text file. When you write a code, and when you write it typically for this or course or for your typical Nighthawk application, you're probably only going to have one file that executes whatever it is you want it to do. Okay, but in reality, programs can get very complicated. I'm using WebEx. If you use Microsoft Office or any of those things are extremely complicated, and in fact usually rely on some sort of system architecture to organize all of the different components of the program. And it could be hundreds of thousands of files and millions of lines of code that are executed. Okay. And how do you actually begin to even write this? I use my favorite editor, which is VI, but you can use anything else you like, Notepad, Emacs. The thing that I'm going to emphasize here is that we should consider using Spyder. Okay? You don't have to. You can use any of these, Notepad, Emacs, or VI. The reason you might want to use Spyder is pretty simple. Okay, Spyder is a development environment, and that comes free with Anaconda. People pay a lot of money for good development environments. So Spyder is not as polished as you would find a commercial application, but so we'll use it. And the reason is pretty simple. It's designed to write programs, so it understands things like programming syntaxes. For Python, it even understands if you start making, simple syntax mistakes, or if you leave out a parentheses here and there, or if your parentheses don't match, or the levels are wrong, it highlights that. So that just makes it very easy and very visual for you to understand if your code is executing as you would like it to go, or if there's things that you need to tweak. There's a lot more to it than that, but at least from the perspective of writing the program, the text editing part, that's the main advantage that you will get with Spyder. Okay. So this is how you begin. Then how do you execute and run your program? So executable is, again, the compiled one for scripting language. It's simply the script. You just run it. If you're using Spyder, there's various buttons and things where you can push, or you can invoke it from the command line. Many ways to do it. Most scientists will use the command line to execute it. But if you've set it up properly, you can just simply double-click it, or if you've written it for an iPad, you can tap it. And in all of those instances, you're executing the executable. You're running it, telling the computer to go ahead and issue these statements. And like I said, on Spyder, there's a button that you push, and it will run the entire code for you. Okay. All right, so I was going to talk about some of the language of programming, but what I'm going to do is skip that and leave it as a reference. and go on to the next couple of topics. We can come back to it if we need to. Okay, so these are some of the use cases that I gave to my NITAR class last time. And I suspect that some of you probably have the same sort of demand or things that you would want to do with a program. And so this is just to highlight what you can use Python for and what my team did last year. So right now you're probably using Excel. Maybe some of you have some programming experience and using something else, but the simplest things like converting one format of data to another one, okay? You would like to be able to take what you get out of the photometry package like APT, convert it into a region file that you can then display on DS9. Those are the sort of things that Python actually is very good at. It can help you do this. The other thing you can do is if you have to manipulate any of this data. For example, if you're applying aperture corrections differently from automatically doing APT or making other systematic corrections, programs are great for that. If you have two different photometry tables that you've gotten from, say, two different bands or two different sources, and you'd like to merge them or compare them at the very least, those are, again, very good. Python is very good for doing, or any programming language. That would be an excellent use of that. Also, for reporting, you can create any number of plots. Just sky's the limit there. And Python has a very powerful set of plotting libraries that will let you do more than what you can do typically in Excel. Okay. And on top of that, you would eventually want to save some of this so you can put it on your poster or in your report. Okay. So I put that in this slide, and last year I wasn't really sure what I could put in there. And this year I was still not very sure of what's not a good programming. But essentially, programs are very good at executing a series of logical operations. That's what computers really are for. If you're writing a novel, obviously you don't want to use that. You just want to use a word processor for that. You can't really write. I know that's not really a really good example of what is not a useful programming. But things that require interactivity, for example, is also not anything you can easily program or can program.
So I have an idea, if I can jump in. If you ever filled out a web form, there's something called a CAPTCHA, which usually has a picture of distorted letters. It is very difficult to write a program that can read distorted letters. So if that CAPTCHA is trying to make sure you're a person. So it's not impossible to write a program. It's just very, very difficult to write that kind of program.
Yeah, that's a good example. That's why I took that picture of the password. It would be difficult for someone to go and data mine that out of it. All right, thanks. All right, let's skip that. We don't need to go through that. All right, so let's go through the basics of the program. I'm going to introduce things like variables and memory here in particular. So variables and your disk that's attached to your computer, those are two different ways of holding data for information. The program also will allow you to access the CPU. That all of that you don't have to worry about at the layer that we're talking about, which is Python. And then, of course, the main thing that it does is it manipulates data. Okay. And then the very last thing is something that we're going to get to probably starting in the second or third lecture. But the very fundamental block of a program is generally a function. And a series of these functions that go together will make a library. So all functions, so at the very basic level, a function may be a unit program a series of instructions, and all they do is compute the average, for example. You can call that function as many times as you like, obviously in your program. But if you have a bunch of these functions, one that computes the average, another one that computes the median, and somebody else, you could put it together and call it your statistical library, for example. So it's a collection of functions. So that's, in essence, that's what program is in reality. You do work in terms of functions. This is how I would advise you. Just the best practice is to break everything down into functions for any of these manipulations. And then you have sort of a master program level that calls and manipulates these functions at will and in the sequence that it's needed. Okay. Now that's what I would say. But this is more what the reality is going to be, at least at the beginning. We will do some functions, but usually we just have a single file and a single master program that executes all of the instructions that we need to accomplish. After you've done this a few times, you're going to automatically realize the usefulness of a function. And then you would start to move in that direction. And I'm hoping that I can instill that in you now, so you would be on the lookout. But it's perfectly okay the first time you write the code is to just have a bunch of instructions that are called at a single level. Okay. Okay, and then obviously once we start there, we can then go into as much complexity as is needed. Okay, you could, and we'll cover some of these things, but not all of them. Okay, mostly we're interested in reading and writing data, manipulating data, and then creating some functions that do our bidding as needed. Okay. Come back to start writing some code in Spyder, but you should comment and be verbose. One advice that I got a long time ago was, imagine if you have to come back to the same code in X number of years, would you be able to understand what you were doing here? If you can, put in enough information that you knew, what your thinking was and what you were trying to attempt, that's good. Okay. Now, it's good advice, and I would say get in the habit. But I have to say that I don't always follow it. I tend to follow it when I need to share this code. But if it's a code that I'm going to be using on my own, I'm quite bad sometimes at following it. Nonetheless, it's, do as I tell you and not as I do, I guess. But comment often and be verbose. You definitely want to test and debug as much as possible. That means, if your program is required to, say, read certain number of certain type of files, you want to push it by changing it slightly. And that's part of your testing and debugging. If it was expecting floating points and in fact it was converting them all into integer values, then that's bad. You want to be able to catch those kind of things, so do test. If, and this is where your own experience will come in after you start writing it, if you find yourself repeating the same operations over and over, that's the time to define a function. Okay. And get used to using naming conventions for files, for programs, and try and keep things simple and easily readable. Okay. At the beginning, I would say, even if you can do this more efficiently by making your code hard to read, don't go that route. Okay. Chances are we're not going to be that concerned with efficiency. Okay. If this sounds weird, I'll just explain it as an anecdote more than anything else. You can write 6 lines to do the same thing, and sort of a Python guru can look at that and say, I can do this in 1 line using these complicated calls, and can write it. But then when it's time for you to go and debug this, you may not understand what was just written. Okay. So keep it simple for now. All right. Let's go to memory. So again, this is at the very basic level, and I apologize if it's too basic here. The thing to understand is that there's 2 different types of memories that we're worried, that we're concerned about. There's the type which is active and live when the program is running, and once the program is done, you may lose it. Most of the time, you do lose it. Okay. And then there's disks, and those are things you can go and buy tons and tons of, and terabytes and petabytes. What you store in disk is there until you erase it or until the disk dies. So you want to use RAM when you're running the code, because access to the random access memory, which is part of your system memory in a computer, is much faster, thousands of times faster than disks. So if you, for example, there's an image, you want to manipulate this image, once you load it into memory, okay, it will take up a few megabytes of your memory out of the few gigabytes that you might have available. But every time you access it and manipulate it, as long as it's in the RAM, those operations are very fast. If you put it on the disk and you try and manipulate it on the disk, so you're reading it from the disk, manipulating it, and then writing it back onto the disk, you'll find that that's extremely slow, and you'll get tired of waiting for it to finish. So you want to use RAM, but the price is that RAM is only available to you when the computer is on and the program is running. Okay? In Spyder, once you define a RAM, you can get access to it. And we'll talk about that in just a minute. But essentially, the takeaway here is that disks are for permanent storage, RAM are for playing around and working and manipulating with data. Okay. The access to RAM is through these things called variables. Okay. They're the elementary elements, they're the elements of the programming language that will sort of reserve and then use parts of your computer's memory. Okay. In the high-level languages like C and lower-level languages, even, you would have to specify them explicitly in size, in the type, and where you want it. But all of those details we don't need to worry about in Python, and that's huge. Okay. You don't know how huge it is until you go back to C or you learn C. How easy Python makes all of that. You don't have to worry about whether you want double precision, quadruple precision. You can simply convert between the two as you need to. Okay. So variables are essentially your gateway into memory. And this is really to RAM. Disks don't really deal with any. Of course, to make programming efficient, there are many different types of variables that are defined. And so, if you're only interested in holding integer values, say your ID number for your star, that takes less bytes to store than a floating point decimal number. So you want to be able to, so you want to specify an integer type of variable to hold the items that would be integer in nature. But of course, if you're storing signal or photometry, you would want to use something like a floating point and the appropriate precision with that. And then, of course, the work of defining how much memory that requires is up to Python and the compiler, and you don't have to worry about it. And it would dynamically, which is as needed, expand or shrink it. Okay, that's really great. Otherwise, you would have to do all of this sort of housekeeping in your higher level language like C, or lower language level compared to Python. Okay? And again, a good practice is to identify what you need and stick it in the appropriate variable. So if you're only going to have a variable that holds a number between 1 and 10, you don't want to define sort of a quadruple precision floating point. I know I'm being silly, but that's just to illustrate the point. Okay. Disks are essentially independent of programs. They're really there to store data in a more permanent manner than you would have in a RAM. So once you're done manipulating or merging the files, you can write it out as an ASCII table, and that goes onto a disk. And then the program, is not really in picture anymore. You can then use any type of editor or any other program to access the same table. On disk, you have as much room as the size of your disk. And so you can go a little bit crazy in that. But again, you still want to stay efficient. The one thing you don't want to use is to think of disks as a substitute for RAM. Okay? They're much, much slower. Now, if you're dealing with situations where you need a terabyte of memory, there's very few computers built that actually have a terabyte of RAM in them. And so in those instances, you have no choice but to use the disk, and you use some sort of optimized input and output code to read and write to the disk. But for anything that we do that you're going to encounter in terms of NITARP or something similar, you don't need to worry about that. Okay. There's an exercise here, which are just to help you sort of think about how numbers relate to gigabytes, and I'll leave that for you. And let me go on to a couple of other fundamental concepts, and we might finish in an hour. Current working directory. This is, again, a concept that will become far more obvious once we do Python itself. But this is, when you write something or when you read something, it's going to go somewhere on your computer. The program is going to find that somewhere on your computer. And that somewhere is your current working directory. Okay? So this concept is something that you have to sort of get used to. Okay? Make sure that you have the appropriate directory connected with your program, because otherwise it could be going somewhere else, and then you have to spend some time finding where, after all, you did all this beautiful work calculating the colors of a particular cluster, and then you wrote it all out, and then you can't find it. Okay? Very basic concept, but something that we should get used to. All right, a few words about Python. The bottom half, I'm just going to reiterate that variables are extremely easy to define and use in Python. In C, you would have to worry about what type it is. In Python, you simply assign it, and Python knows by looking at it what type it is. Okay. So it does a lot of thinking for you. Then I spent some time emailing you about Anaconda, and there was a reason for that. If you were to just download Python with sort of the bare bones, no frills, basic, it's actually not as useful. And people have spent a lot of time building up on that with useful libraries. And this collection of libraries in the Python in a distribution like Anaconda is what's really useful for me and for you. So bare bones Python comes with Mac OS, and if you didn't have Anaconda installed, you could just bring it up and start playing with it, but you won't find it as useful. Okay, so I highly recommend. We're going to use Anaconda, but really that's what we're going to be. That's what you're going to need anyway to do most of of what you would want to do with Python. Okay. So there's I'm extolling some of the advantages of Anaconda. And finally, here is Spider, but I can show you a much better view because I had it up, and just to show you what this looks like. But this is, at this point, you should be able to bring up a window of Spider if your installation is correct. And I'll do a little roundtable to make sure that you guys all have it. But as Spider, this I don't know why they call it Spider, but it's a very useful programming environment. And actually, I'm using it, so you see some of my code here. But in a new code, it will give you a nice editor window, which is this part over here on the left. And you can make it as big as you like, as small as you like. But it would allow you to do some very simple programs. And if you're doing something wrong, it will start telling you. So, for example, if I say I want to add 10 to 23 and then multiply it to 3, and then left one parenthesis but not the other one, it comes up, and then you will actually have some statements. Sometimes they're helpful, sometimes they're not, but notice that the parentheses turned green once I got the right set of parentheses on there. Okay? So it's sort of listening to you as you are, or it's watching you as you are creating your code, and it tries to be helpful. Sometimes it's a nuisance, but it does try to be helpful, and it's an improvement over just a simple text editor that you can have. Okay, so you've got an editor, but once you're done with the editor, you have various ways that you can execute this, and we won't go over this in detail. Oh, yeah, of course, it's going to want me to save that first. But it also gives you the Python compiler. So this part over here in the bottom right, this is the compiler that's constantly running. And when I type it in the editor, it's not executing yet, but in the compiler, it is. And every time I type it in the compiler, it executes. You get the result. And hello world. Whereas here I can say hello world, and I have to wait until I run it before it would actually do it. Okay, so I didn't set this up to run it. I didn't need to. Okay, so when I do that, I don't need to save it, but it executes the code for me, and I get the hello world this way. Okay, we'll go over this again when we start typing and creating code. The top right portion, we're not going to worry about too much. It's helpful, and you'll see how it becomes helpful, and it's essentially going to allow you to get to some of the help functionality available for Python. And it tries to do that in an easy, user-friendly way. But this is the part that hasn't been well developed so far. Okay. There's other aspects of it that are far more useful, and we'll go over those in the next lecture, most likely. Okay, so I think that's the sum of my slides here. Yes, it is. I left out sort of the thesaurus, or not the thesaurus, but the dictionary. You're welcome to go over it, and if any of those are unfamiliar, let me know. Where is it? Okay, so questions, or does anybody want to discuss their Python installation or how to start Spider? For me, this is how I started it. I don't know if you can read this. right here, I issued the command spider on the command line. You can also go to your applications, I believe, and oh no, I would have to find it. I never use it that way. But okay, so I can go under my binary directory. And in here is Spider. If I double clicked on that, it will start Spider for me. Okay, who's this? Okay. Okay. So I know that the launcher is one way you can do it on the Mac. Anybody else had problems running Spider? There's Spider on my computer. Okay, so we are all set with Anaconda and everyone's ready to go. And most of what you heard today was
Actually, I didn't know a lot of what was on today, so I really appreciate it. Step back. Start slow.
okay.
I didn't know any of what was over today, and I'm going to sit down and just read through this slowly again.
Okay, that's really good to know. I'm still trying to get at what the proper level is to start with. So I just assumed that you know no one's programmed before, ever, or really thought about what programs are. Okay, any questions on the material? And I mean, it really sounds like no one has any problem with the with the actual installation or getting to the Spider screen. Okay, then let's call it quits here. I'm going to stop sharing my desktop and let's see. We acquired new people in the presentation. Okay, everyone. Well, you can email me if you start looking through the slides again and find something confusing, or if you have any of the obviously questions about the two assignments or anything else with Python. I'm going to be working on the next level, and hopefully in the next level you actually get to do some Python or write a code at the end of it. But let's call it quit, and I'll same time next week.
Thank you.
Okay.
Thank you very much.
Okay. Bye-bye.